Hello and welcome to the Introduction to Logarithms video. First thing you might want to know is, what is a logarithm? Well, we've been spending so much time with exponential functions and solving with exponential functions that if I gave you something like this, you'd say, oh, I'm going to change this 9 to a base of 3 and then use my exponent rules to solve. However, what if instead of an 8, instead of a 9, what if that was an 8? What would we do? Because we cannot change this 8 into something with a base of 3. Well, in that case, we would have to use logarithms. Now, logarithms are the inverse of exponential functions. I'm going to use an exclamation point there because that's a really big piece. Logarithms are the inverses of exponential functions. So when I think about inverses all the way back in February when we started learning about those, things I think of, my x and y's need to switch, whether I'm solving through composition, whether I'm solving through switching my x and y and solving, or whether I'm looking at a graph. So let's look at a graph. I'm going to pause this video to bring up an image. All right, so the image I've brought up is of an exponential function and a logarithmic function. So if we take a look at this kind of purple graph right here, and right here I can see, okay, this is 2 to the x. This is the exponential graph. Now if I do 2 to the power of 2, or pardon me, 2 to the power of 1, I get 2, 2 to the power of 2, I get 4, 2 to the power of 3, I get 8, and so on. So we see this graph here, which we've spent some time working on, and you can also see that the horizontal asymptote is y is equal to 0. Now, when we are graphing inverses, we can either look at the table and switch our x and our y, or we can, I see there's a mistake there. We can reflect over the line y is equal to x. This should say x. I'm going to fix that. There we go. We can reflect over the line y is equal to x. And once we've done that, we end up with this green graph, or this green table with log base 2 of x. I'll talk about the pieces of a logarithm in just a moment, but the main point is here that this graph right here, this logarithmic graph, is just a reflection of our exponential graph, or like we said, the inverse. And now instead of having a horizontal asymptote, we have a vertical asymptote at x is equal to 0. So they are inverses of each other. Now, unfortunately, this year we've had to cut graphing with logs. However, we will still be doing lots and lots of solving and story problems. So when we go into solving, just like how exponents have a lot of different properties, so does logarithms. And they're all very similar because, again, they are inverses. But when we're looking at logarithms, you heard me mention the word base before. Let's look at the components of a logarithm. Well, a logarithm, or we'll often call that a log, I'm going to change that to black. Often call that a log. There's always something inside the parentheses, and it's always going to have a little base down here. Now, if it doesn't say what the base is, we are going to assume that the base is 10. So again, this is the base. Most calculators only know how to deal with a base of 10. Later next week, we'll be learning how our calculators can figure out how to deal with bases other than 10. So that's going to be our base, and then anything inside that parentheses is going to be our argument. So we have the base and the argument. These are the features of a log. Not a whole lot today, but a little bit more next week. We're going to learn a lot about natural logs as well. So natural logs will be ln. You'll also see that button on your calculator. It'll be ln, and a natural log has a base of e unless otherwise specified. And e is kind of the compound of so many things adding up quicker and quicker and quicker. And like I said, we'll talk about that a little bit more, but e in this case is still the base, x would be the argument, but mostly we'll be dealing with logs. So let's look into just some of those log properties. The first property isn't so much a property or a rule, it's more of just a rearrangement. Like, how if I had given you, the example from before, how would we change that from exponential form to logarithmic form and back again? So that first rule, or rearrangement, says that log base b of a, so log base b of your argument a is equal to e. So that's kind of our general setup of a log. It's equal to something. We can say that that can turn into base b, make this uppercase b, base b with your exponent e is equal to a. And you can go back and forth on both of these for this rearrangement. Now, when I think of this rule in my mind, I call this the log-bay rule, because it helps me remember the order of my base, answer, and exponents. When I turn it into my exponential form, that's my base, my answer, and my exponent. So for instance, if we had something like log base 4 of 16 is equal to 2, well, this is log base, answer, exponent, or log bay. So we could turn this into 4 to the power of 2 is equal to 16, or my base, my exponent, and my answer. So that's going from the logarithmic form to the exponential form. But like I said, you can also go the other way. So if I gave you 3, oops, sorry, that's supposed to be in blue. If I gave you 3 to the 4 is equal to 81, this is my base, exponent, and answer. And I want to turn this into log bay. So this will become log base 3, my argument of 81 is equal to 4, or log base, answer, exponent. So again, you can use this rearrangement in either direction. We'll spend a lot of time practicing that, as well as some of our other rules. Our next rule or property is the product rule. And it says that if we have log base b of m times n, or two things multiplying to each other inside the argument, we can separate those out into log base b of m plus log base b of n. Similar to our exponent rule, where if we have two numbers of the same base being multiplied together, we would add their exponents. Similar type of rule. So if we were to practice and say, how would I separate log base 7 of 5x? Well, I could say that could be log base 7 of 5 plus log base 7 of x. Or if I was to go the other way and have log base 3 of 2 plus log base 3 of y, I could then go backwards with the rule, add the insides, and bring them into one log, and say that this was equal to log base 3 of 2y. So since that is similar to our product rule dealing with exponents, you might guess that the quotient rule is also similar. So this one's saying if we have log base b of m divided by n, well, with our exponents, if we have two numbers of the same base being divided from each other, then we would subtract their exponents. So that's how we're going to separate this out. We're going to say that we have log base b of m minus log base b of n. So I get those aren't really super lined up, but that's kind of where we're going with this. All these rules are very, very similar. So if we had log base 5 of x divided by 9, we could separate this out into log base 5 of x minus log base 5 of 9 and expand it that way. Or if we wanted to condense and simplify, if we were to start with something like log base 2 of 10 minus log base 2 of 12, again, those bases have to be the same, 2 and 2, then we could have log base 2 of 10 divided by 12 and bring them together. So with any of these rules, properties, rearrangements, whatever you want to call them, they can go in both directions. So like I said, logs has a lot of rules and properties. We're only going to go over 3 more in this video, but make sure you practice these as much as you can. So the next one is our power rule. Again, we also have one of those when dealing with exponents. So for logarithms, our power rule is that if we have log base b of m to the n, or something with a power, we can bring that exponent to the outside and have n times log base b of m. So we're taking it out of the exponent, or pardon me, we're taking it out of an exponent and we're making it a coefficient. So that's like saying if I had log base 5 of 2b, I could bring that b to the outside to be a coefficient and be b times log base 5 of 2. Or we can go the other way, and if we had 8 times log base 5 of x, I could bring this 8 to be an exponent and have log base 5 of x to the 8. So again, all rules go in both directions. Our next 2 rules don't actually have official names, so I'm just going to call them shortcut 1 and shortcut 2, but it's just ways of canceling out logarithms that I think that you're really going to enjoy and hopefully you've seen before. So shortcut 1 says that if we have log base b of b to the m, where the big base inside the argument and the little base of the log are the same, we can cancel out the log and the bases, and we're just left with whatever that exponent is. So if we have log base 11 of 11 to the power of y, we're just left with y. The bases cancel out, log goes away, it's just the exponent. Or for some reason, if we had to go the other direction and you just had 4, well, 4 could be log base 13 of 13 to the power of 4, or the bases of 5 or 12 or whatever you want. But as long as the little base and the big base are the same, you're good. Now our very last shortcut says that if we have a to the power of log base a of b, so again, dealing with 2 different bases, dealing with exponents, but now just set up differently. Again, if this big base and this little base are the same, we can cancel those out and just be left with whatever is inside the argument, in this case, b. So if we had 5 to the power of log base 5 of x, since this big base and this little base are the same, those go away and I'm just left with x. Or if we needed to go backwards for some reason, if I had y, I could say that's 7 to the power of log base 7 of y. So those are just kind of quick shortcuts to either change something into a log or get rid of a log. But here are some of the rules and properties of logs. In the Go formative for tomorrow, you will be discovering these yourself. So if you've watched this video, you've definitely given yourself a leg up. So if you have any questions, please let me know, and I look forward to seeing you tomorrow.